So when you are using the Molière chart fronts already I have told you. Once more I will be telling you that please see that you can mark the points correctly in the Molière chart, because in this paper for second students we need to take the help of both the Molière chart as well as the help of the stream tables. Then only we can solve the problems. Okay. So once the situation comes under control and once we get chance for some one or two offline classes, again I will be explaining you in the offline classes also regarding how to make use of the Molière chart, and when you're using the Molière chart, how to note down the points, that is the entropy, enthalpy for the various conditions. Okay. So we'll wait for, or no, shall we wait or shall we start discussing the today's things now? I think previous class was calm. Sir left early or sir had to till up till last minute also?
Left early, sir.
Left early. Okay. So then we shall start discussion of the today's class. Okay. Homkar has joined. Hope my screen is visible to you all.
Yes, sir.
Sorry, due to network problem, I had got disconnected. Sorry, students, due to network problem, I had got disconnected, and again I have joined the session. I hope my session is visible to you all clearly.
No, sir.
1 minute, I shall start sharing the screen. Is it visible now? Is it visible now?
Yes, sir.
Okay. So today morning's problem, just we had discussed some points and I had given you the homework. So just I will complete the problem so that you can understand what are the steps required to get the final solution of this particular problem. Okay. So as discussed in the morning's class, students, I had said that there is an ideal regenerative cycle, and the high pressure turbine, it is receiving steam at how much? 20 bar, 300 degrees Celsius, and this steam at 20 bar 3 degrees Celsius. If you make use of your molar chart, you need to mark the point, that is the value of enthalpy H1 and S1, okay, at 20 bar 3 degrees Celsius. So as I said, in your molar chart, what you can do is, just I am showing you a small representation at the side of the problem here. So this is your molar chart, this is your saturation line, it is like this, and now we have got the value for 20 bar 300 degrees Celsius. So imagine this is 20 bar pressure line, and you are having some 300 degrees Celsius temperature line like this. So wherever these two pressure and temperature lines meet, we call this point as point number one. This is point number one, students. Okay. So from this point number one, you can note down the value of H1 on this side, as you move downwards, you can plot the value of even S1 also. You get the value of S1. Right. Then the next it has said that after the expansion to pressure of 7 bar. So 7 bar, when as you move through along this line to the downward, students, you should search for 7 bar pressure line. So the 7 bar pressure line, somewhere it comes here, students. Imagine this as 7 bar pressure line. So wherever it cuts this particular line, mark this as point number 2, and you can note down the value of H2. Note down the value of H2. And now, students, again from this 7 bar pressure line, what you should do is, you shall start reheating. So it has said that reheating is done up to how much? Again, 300 degrees Celsius temperature. What it means is, along this pressure line itself, 7 bar pressure line, you should move upwards where it cuts the temperature line of 300 degrees Celsius. So somewhere here it cuts. This is position number 3. You should check. So for this value, how much is the value of H3? You should note down H3, and from here, if you move downwards, you will get the value of S3. Just I am showing a rough sketch. You can do in a molar chart. Just I am telling you how to mark the points. Okay. And then, as I said, after this point number 3, it says that there is an intermediate pressure turbine of how much? 1 bar here said. So after 1 bar, you need to come downwards, and at 1 bar, you need to note down the corresponding pressure and temperature. One important point, students, I would like to tell you is, if the pressure of 1 bar, if it is coming below saturation line, ಅವಾಗ ಏನು ಮಾಡಬೇಕು ನೀವು ಅಂತಂದ್ರೆ, you should take the help of your steam tables. Steam tables help ತಗೊಂಡು, you should find out the value of dryness fraction, and then you should find out the corresponding enthalpies and entropies. So after 1 bar, another pressure line has given the question, that is how much? 0.05 bar. So this also comes in the wet zone itself, which means ಇದನ್ನು ಕೂಡ ನೀವು ಏನು ಮಾಡಬೇಕು, using steam tables you have to find out the value of enthalpy as well as entropy. So H1, S2, S3 can find out directly molar chart, but the things that is the other points 4 and 5, you need to take the help of your steam tables and get the corresponding values. So as I said, this is the sketch of the TS turbine, which you can see here, and as I said, some amount of steam is taken for the reheater. Say it as M1 mass, so remaining 1 minus M1, it travels here through the condenser. Once again, it comes and meets here at position number 8. So you need to make again what? As morning we have discussed, that is mass and energy balance. You need to calculate to find out the value of M1, so that you can find out the corresponding enthalpies, H5, H6, H7, etc. things. You can go on finding the things. Okay. So now, as I said, from your molar chart, at a pressure of 20 bar, temperature T1 is equal to 300 degrees Celsius, you can get the value of enthalpy. See here, he has found enthalpy as 3025, similarly entropy as 6.796. So they are taken the help of tables, or you can take the help of molar chart also. You can get. Remember, students, in the examination it is not said mandatory to follow any method. You can whichever is easier for you, you can start that method also. So in here they have done using both steam tables and molecular chart, so no problem. You can take any of the methods and get the things. Then similarly, as I said, from there what happens from 1 bar, sorry, from 20 bars, it goes expansion up to how much? 7 bar. So for a pressure of 7 bar student, 7 bar, wherever it comes downwards, wherever it meets which pressure line, wherever it meets the pressure line 7 bar. So for that, you have to find the corresponding enthalpy. So this you cannot do in the stream tables. So particularly point number 2, you should take the help of Molecular chart itself. So you can see here H2 is equal to how much they have found out, 2794 kilojoules per kg. Now from here, we should move along this pressure line itself, where it can touches again what 300 Celsius temperature line in the molecular chart, where you will get the value of H3. So H3 and S3 again they have calculated. So as I was saying you, 1, 2 and 3 are the superlated zones, so no doubt you will get them directly the values. But the other points they will be coming in the two-phase region, that is mixture of steam and water particles, and that is the reason we need to find out what dryness fraction. So here you can see here from the table and velocity has got S3 is equal to this particular value. But S4 and S5 students, you cannot find them directly. You need to find out what dryness fraction S4, that is X4. Similarly for S5, you need to find out X5. We take the help of the steam tables. So let us see how we have done that one. As I said, 1 bar, that is point number 4 students. If you observe in your TS diagram here at this particular point, ideally the saturation curve which means it is a mixture of water and vapor particles. So at 1 bar here from the steam tables, these are the data which is taken from the steam tables. This data what you are seeing here, it is taken from the steam tables. You can see we have written table A1 also. They calculate and get the value as how much? X4 as 0.99. Make one correction students. This is HF4, not HF3. It is HF4. Similar this is HFG4 also. So therefore, HF4 is equal to what? HF4 plus X for HFG4. So those values are substituted here. 417.5, 2257.9. Dryness fraction value, it is only 0.99. So after calculating what we get H4 value is how much? 2652.82 kilojoules per kg. Similarly, I go for finding the next position, 0.05 bar students. So for 0.05 bar, from the steam tables, we are finding SF5 value, SFG5 value, HF5 value, HFG5 value. I equate and get the values as X5 as 0.8615. So as it is going downwards, the dryness fraction value, it is reducing, that is 0.8615. Similarly, enthalpy will reduce, it gets it as 225.9 kilojoules per kg. Okay. So like this we have found out H1, S2, S3, H4, H5. Similarly, S1, S2, S3, S4, S5. Which means students, if you observe carefully, the right side parts, we have found out all these things. H1, S2, S3, H4, H5. Similarly, S1, S2, S3, S4, S5. These much things we have calculated. Okay. I hope these things are clear to you. Now what we shall do is we shall find out the next other parts calculation part, that is we shall move to the other side of the TS diagram. So H8. So how you can write students, H8 means what? If you observe in the TS diagram carefully, so this is your part 8. So where this point 8 is located completely on this curve, which means it is in the liquid phase. How much pressure it is? 1 bar. So HF8 is equal to H8. 1 bar value HF, whatever is that, is equal to H8. Similarly, if you go for position number 6, it is on which pressure line? 0.05 per pressure line, which means this is equal to HF6 is equal to 137.8 kilojoules per kg. So now pump work. So here is one pump, here is another pump. So pump work we are finding. So pump work for the first phase is nothing but this one, that is from 9 to 8. So I write it as VF into P9 minus P8, which is this particular value, or X9 minus H8. So therefore, I get it as how much students now? H9 as 419.48 kilojoules per kg, that is H9. Similarly, now I'll be finding for the second case, that is here. This is second pump work. We have 6 into we are writing the things and we are calculating it as pump work as how much? 0.095 kilojoules per kg. So now total pump work. This is one pump work, this is one pump work. So total pump work, how I can calculate it? I can calculate this as 1 minus m1 into WP2 plus this is only mass is how much? It is only m1. Okay. So I am recombining here and I am writing this as in this fashion, students. WP1 is nothing but it is 1 minus m1 h7 and WP2 is 1 minus m1 WP2, that is h4, which is equal to h8. So now what I can do is I'll substitute the things here, that is h7, h4, h8, and I'll find the term mass. It is how much? 0.11 kg per kg. Sir has left here, you write here per kg. So finally, pump work WP, I write it as in this form and I get the value so much? 419.56 kilojoules per kg. So this equation, students, what you are observing here, this is what? This is mass energy balance equation. Mass we are equating the mass. So at point 0.8, whatever the input terms are, the H8 is equal to, it is summation of what? This term 1 minus m1 into h7 plus this is m1 into h4. That I am equating here is equal to h8. So I am getting the value of mass m1 and finally pump work as 419.56 kilojoules per kg. So now, after this, if we calculate carefully, students, we get the turbine work. So turbine work is what? H1 minus H2 plus H3 minus H4 for 1 kg. Then H4 minus H5 is what? There is a reduction in mass, that is 1 minus M1. So that I am taking here. So I get the total value of turbine work. The net work is turbine work minus pump work. We'll get the net work done. So finally, the heat supplied. The heat supplied is what? It is from the heat supply is taken from this particular region. That is H1 minus H9 plus H3 minus H2. This is the amount of heat supplied. So apart from this, we get the thermal efficiency as how much? 20.83%. So you can see using the reheating method as a regeneration method for this particular conditions, the thermal efficiency has reduced to how much? 20.83%. Then this is one new term, students, that is specific steam consumption we say. So this is the thing what the network done. If you take it with respect to the time for 1 hour, 3600 seconds, the value you get in terms of kg per kilowatt hour. And quality of steam entering the condenser already we have calculated, that is 0.8615. These are things which are dealt in this particular problem. Okay, I hope these things are clear to you. I'll be sending the notes today evening itself. You can work at your home also.
Yes, sir.
Now, characteristics of an ideal working fluid. This is very, very important. Yes, somebody is asking something. Yes, you have any doubts, you can ask. If you have any doubts, you can ask. ಏನಾದರೂ ಗೊತ್ತಾಗಿರೋ ಕೇಳಬಹುದು ಯಾವ ಸ್ಟೆಪ್. You will go once more backwards. If you want, you can ask which step you have not understood. See, once again, I am going backwards. If you have not understood any step, you can ask me. If you have any doubts in any of the steps, you can ask and get clarified, students. Don't hesitate. Any steps you haven't understood, you can ask and get clarified. Okay, then I think we shall move further. So as I was saying, this is an important question from an examination point of view. Many times it is asked in the examination, write the characteristics of an ideal working fluid for 4 to 6 marks. So here are some of the points which you need to understand. That is the first important point. What it says is, for always when a vapor is working in a steam power plant or for vapor power cycle, the very very important point is the first point. It says the working fluid which you are using, the working fluid. So generally now you are using water as a working fluid, but if you are using any other fluid other than water, you should say that you should know its critical temperature. This is a very very important term. You should know that you should identify its critical temperature. Hello students. Sorry for network problem. So I would ask you once more. Yeah. So is my screen visible to you all?
Yes, sir.
Once again, I will be discussing these points regarding characteristics of an ideal working fluid. So please listen, students. As I was saying, the first important point is that whatever the working fluid you are choosing, now we have learned that in the vapor power cycle we are using water as a working fluid. So if you are using other than water as a working fluid, you should see that you should know the critical temperature of that particular fluid. So why is it is important? Because you have seen that for our steam, when you are using as a working fluid, the boiling point at the atmospheric pressure is how much? It is 100 degrees Celsius. Similarly, if you go for another fluid, you should know its saturation pressure along with the maximum permissible temperature, which is relatively lower in conditions. And along with that, you should know that you should have large enthalpy of evaporation at that particular pressure. This is the first very, very important point. Second important point is that whatever the heat rejection takes place, that heat rejection which is occurring at a particular saturation pressure, it should be always above than the atmospheric pressure. Otherwise, what happens? There are chances that choking may take place or a vacuum formation may also occur. So, to avoid this, you should see that the saturation pressure of the heat rejection should always be greater than the working fluid atmospheric pressure. Then the third important point, so as it has been discussed, that the liquid which you are using, the specific heat of that liquid should be as small as possible. Why this word is said is, if the phase change occurs and specific heat is very high, sometimes it becomes difficult for the working fluid to pass through the entire whole parts, that is from boiler, turbine, condenser. So that is the reason that it is said that the specific heat of the working fluid which you are choosing, it should be as small as possible, as lower as possible, so that heat transfer can is used to raise the liquid to the boiling point with less amount of time. This plays a very important role. Then similarly, it is said that the saturated vapor line of the TS diagram should be steep, very close to the turbine expansion process, so that The excessive moisture does not appear during expansion. So what is the meaning of this particular point is, so just I'm drawing a small diagram here. This is your saturation curve, students. So the expansion of the steam water takes place, it should be in this form. Okay. So as and where the saturation upper line of the TS diagram is very steep, very close to turbine expansion process, then what happens? There is the possibility of moisture that can reduce to much greater extent. If the moisture is more, then what happens? The problems of rust formation occurs, corrosion takes place. These are all things which are causing a problem for the turbines. That is for the Rankine cycle. Then another important point is the freezing point of the fluid should be below what the room temperature, so that this is not the case, then what happens? The water which is flowing through the condenser, suddenly if there is a temperature drop, then it may go to the formation of solidification, that it may go for ice formation. So the freezing point of fluid which you are choosing, it should be below the room temperature, so that it doesn't get solidified when it is passing through the pipelines. This is a very, very important point. Fifth point, this is. Then sixth point, students, very, very important. It should be chemically stable. Chemically stable means what? Whether it undergoes phase change, that is from liquid to vapor or vapor to liquid, there should be no chemical reaction. Chemical, it should be stable. So therefore, you should use that part of fluid along with that when it is coming in contact with the metals. So we are saying that it is a closed cycle. Completely, it is going from boiler, turbine, everywhere. Different types of parts are coming into contact with that particular working fluid. So it is coming into contact with the particular working fluid. How the working fluid should not go under any changes, chemical reactions in our, which means it should be chemically stable at any point of temperature, pressure, and other conditions. Then the seventh point, it states, students, that the fluid should be non-toxic, non-corrosive, non-excessively viscous, and easily available. Non-toxic, why it has said is, sometimes suddenly there are some accidents in the thermal power station, and if there is any leakage, so automatically the people who are working there, if it is toxic in nature, then they may die suddenly. So the working fluid which you are using, it should be non-toxic in nature, non-corrosive. That is, the lifespan of the metal parts is very good. If it is non-viscous, it flows very easily and should be easily available. So then only you can prefer installation of the thermal power stations using this Rankine cycle as your main part. Okay, so these are the things which I wanted to discuss. So this completes, students, your module number 3. I'll be posting the notes in the Google Classroom itself. You can go through the notes. If you have any doubts, you can send me the message personally through the WhatsApp, or you can discuss in the tomorrow's class also. Okay, I hope we should, already it is too late. So if you have any doubts, you can ask, or you can exit from the class also. You can exit one by one.